if you didn't pick up from that, I'm one of those wicked, abhorrent engineers, and I hope to show you that our contribution goes beyond engineering, and as the previous two speakers have both said, more and more nowadays involves an interdisciplinary approach to either engineering solutions or, more likely, community solutions. So my areas of interest have always been centred around water-sensitive urban design, but over recent years, and particularly permeable paving, I should say, and the focus of what I'm presenting today is largely about permeable paving. But the more I've progressed through my career, the more I've realised that my attempts at engineering a good solution absolutely are dwindled by the power of natural systems, and particularly vegetation. So I can't design anything that approaches the ability of a vegetated system to remove pollutants. I can try to, and I can assist it, but I can't actually mimic it that well. So the more I've progressed, the more I realise that I need to use these systems. And that's really shaped my research. So my research has evolved from being water-sensitive urban design, more into green infrastructure, and more recently into the climate change impacts on water systems, and they're huge. And that's where some of these vegetated systems come into their own. A permeable pavement by itself doesn't capture carbon. It doesn't, unless you can keep the water close to the surface, doesn't really mitigate urban heat island effects terribly well by itself. Although there are systems that you can act that way. But what we try and do when we do that, when we try and mitigate urban heat island effects, is really, when you think about it, we're trying to mimic what all vegetation does. The evapotranspiration process is what we're trying to mimic. And we can do it to a certain degree, but we can't do it anywhere near as well as the vegetation itself. So you might just say, well, why don't you just forget all the engineering solutions, and why don't you just plant, just put everything vegetated? It would be lovely in an ideal world, but as Peter pointed out, that's never going to work, first of all. And secondly, it doesn't actually solve your problems. You still have floods, you still have water quality issues, and you still have a need, if you like, to generate more water. As Shelley pointed out, our water resources are diminishing. So you do need those engineering solutions, but the key word that I think both previous presenters brought in was integration. How do you integration? How do you create a happy marriage between a natural system and the engineering or hard engineering solution that you, did that very well, a hard engineering solution that we've relied upon in the past. And that's what I'm hoping to focus on. I was in a conversation with Rob yesterday from the Arbor Centre, and a big thank you to the Arbor Centre for putting this on, and this is a fantastic turnout. Thank you everyone for making time to come today. I was in the similar conference last week in Adelaide, and we were quite pleased that we got just over 55 people turn up, and like today, a real mix of people from local government, engineers, arborists and landscape architects in particular. But to see this crowd here today, it just reminds me of the last time I gave a presentation in Perth, which was in 2014, where I was working with the CMAA promoting permeable paving, and I remember, it wasn't in this venue, but I remember WA was our biggest crowd. So a big thank you everyone for coming today. Sorry, I just want to, in that conversation I had with Rob yesterday, we were talking about the challenges that society face, beyond what we're looking at today, water-sensitive urban design, which is very important, but the really, really big societal challenges, climate change, water scarcity, population growth. Think about any one of those, and there's probably 5 or 6 others you could think about. Name me one of them, any one of them, that sits comfortably in one discipline. That if we're to solve them or even have a crack at them, we're going to rely on just one discipline, arborists, or engineers, or scientists, environmental scientists, social workers. None of them will have a cat and hell's chance of making a major contribution by themselves. They have to work together, and those problems are becoming deeper and deeper. And I'll just use climate change as an example of those 3, because it brings in many of the concepts that we're trying to achieve here. So if you look at climate change, for instance, the science is, I'm not going to bore you with the science, but the science is there, it's absolutely happening. But when you actually look at the figures, it is quite frightening. The mass extinctions that this planet has experienced have all been caused by single, what we call carbon events. So the Great Die-Off, which happened 252 million years ago, was caused by a release of carbon. If you look at the long term and what happens in between, there's been 4 or 5 of those mass events, but that was by far the largest. It killed 81% of all marine species and 70% of all vertebrates. And fortunately, the vertebrates that survive are mammals, and that's why we're all sitting here today, because that's what happened in that event. Now, I'd like to bring that forward to today, because it took the Earth 2 million years to recover from that one event 252 million years ago. Right? I argue that where we are today isn't far off one of those events. Because today, remember that 2 million, remember 252 million, where we're at today, if you measure the carbon dioxide in the atmosphere, it's 417 parts per million. The last time it was above that figure was 3 million years ago. So we are dangerously close to causing a huge problem. And I'll come back to the carbon issue because the volcanoes in the world are the regulating factor that bring carbon from the Earth's mantle and put it into the atmosphere. If we didn't have that, there would be no life on Earth because this planet would be far too cold. Okay? We're here because of carbon dioxide. It's a good thing in the atmosphere. But we are currently putting into the atmosphere 100 times more than all the volcanoes on Earth every year as humans. So unless we do something about that, it's just going to get worse and worse and worse. The planet's going to get super warmed, and a lot of the vegetated systems we're trying to build today simply won't survive, nor will many of the animals. So these are bigger issues than what we're trying to address today, but they are actually closely interlinked. Because of what we do with our water, what we do in terms of cooling our urban environments, all makes a very important contribution. Sorry to start so glumly. Okay, so I've been interested in and have worked with arborists such as Tim Johnson, who you'll be hearing from later today. But there's been a very recent study, literally in the last few months, in fact, that's been released from the City of Adelaide on what it takes to plant a tree in Adelaide. And those on the right-hand side are all the offsets that you have to adhere to. And notice gas is the only one that has 2. It can decide whether it's 0.5 metre or 3 metres. The legislation is very vague. Water has 2, but one's water and one's sewer, and electrical's in there. So if you want to plant a tree, that's what you have to go through. And the actual flow chart that the City of Adelaide uses for planting a tree is shown on the left-hand side. To read it costs money, okay? To actually go through it, it's incredible. That's to plant one tree, okay? And they've recognised that this is a problem. You've got to bear in mind the authors of these reports work for City of Adelaide, okay? And I'll go through some of their recommendations in just a moment. But if you look at those boxes at the top right-hand side, or look at the right-hand thing, you basically spend a lot of your time consulting with people. And another comment that stuck with me from what Rob was talking to me about yesterday was, I thought I dealt with trees. I don't deal with trees, I deal with people. Okay? And that's a very, very telling remark, because a lot of our time is spent bringing together. And I'll also refer back to something Shelley had in her presentation, where she had those little figures. I think Paul drew one of them. And there were lots and lots of people all together. When I design a permeable paving system, or I get an engineering company to design one of the first things I tell them to do is to go out on site and watch it being built. Because if you don't, once it's finished, it's a bit like a tree, once the tree's planted, you don't actually know what's underneath the surface. You can't lift those layers up and look. You don't know whether the contractor bedded it on your specified gravel, 3 to 7 mil gravel, or whether they actually bedded it on sand, because the last 99 projects they did, they put normal pavers onto sand. You have no idea unless you go in and dig up some pavers. And it's the same with any system like this. So if I struggle to get an engineer who designs a system to go out for half an hour to watch it being constructed, see the important parts, how am I going to get 5 specialists? How am I going to get Rob in a room without paying him? How am I going to get an engineer in the room without paying them, an ecologist, a social scientist? How am I going to do it? It's not that easy. But Shelley was right, it is the best way. So what we have to do is break down the systems we currently work in, and we have to bring people together and work out a sustainable way of communicating to each other about what's important, what can maybe be let go a little bit of, and get people's advice and value that. The problem with that is we all speak different languages. So engineers need to know a little bit about arboriculture, and arborists need to know a little bit about designing a permeable paving system. And social scientists, unfortunately for them, need to know a little bit about everything. Okay? So that's the challenge we have, and it's a big challenge, because in my career, and I've been trying to push this for quite a long time, I've had very little success. I think the way that we design things today, we've got more tools, and Peter touched on that, and I agree with him entirely, we need more still. But the way we do things fundamentally hasn't changed. And as Rob and I reach the end of our careers, that gives us a lot to reflect upon about whether we have actually been effective enough. So Rob's way of doing that is to bring you guys together, and hopefully something will come out of this where we might say, let's not work as a consenting authority and a design team and a developer. Let's all sit down and get a good outcome for the community. These are the recommendations from that report. Now, unfortunately, one of the authors was a researcher like me, so you'll see that spend more money on research comes up in 2 of them. We just can't help ourselves. Okay? But the number 1, by far, the strongest point they made was you need good legislation to help. You always think of legislation as being a consenting type thing, and it's there to stop you doing things. Good legislation is not like that. My experience with government has been that policy always lags innovation, always, unfortunately, but it always catches up. Okay? And the purpose of policy and legislation is not to punish, it's to support. Good legislation supports. So we all need to work towards getting the right framework in place. Now, I'm not familiar with the WA systems, unfortunately, but even in Adelaide, where we do have some legislation, it's inadequate. And the City of Adelaide recognises that totally. So the number 1 recommendation is get supportive legislation in place. And that's not easy. Number 2 is decision-making standards for trees, not surprisingly, and I think that's done differently in different states, but overall it's generally a good thing. R&D into urban forest development. Collaborative and well-informed decision-making's there. Funding to support that research and development that they covered off in point 3. And planning for trees in the long term. Now, Adelaide is going through, I've lived in Adelaide for the last 15 years, and 15 years before that I lived in Sydney. In those 15 years in Sydney, I watched development rampage through Sydney, not surprisingly. I migrated to Sydney in 1991, population was just over 3 million. I left there in 2015 and the population was over 5 million. I landed in Australia in 1991, population was 16 million and today it's over 26 million. You are in one of the fastest growing developed nations in the world, here in Canada. Okay? So the idea that things are going to get easier in terms of urban development, forget it. It's not. It's going to get harder and harder and harder. There's going to be less and less space. That's why you're in such an unregionalised country, because it's cheaper to put all the infrastructure in 5 big cities than it is to spread it out like they do in most of Europe. Okay? We will get to that point where the population is such that you will have to be building other cities and other regional centres. But ultimately, what we're going through now is not an abnormality, it's the norm, and it will remain the norm. So our challenge is to build for that and to design for that, and it's not easy. So I mentioned that I've been working with trees. This is the first system I built when I came to Adelaide in 2006, and that's what it looked like pretty much soon after that. That's before the paving's gone in, but basically that's a bioretention system designed to take runoff from a car park. But unlike the bioretention systems, if you want to characterise the work that we do at UniSA compared to, say, the work that comes out of Melbourne, all our bioretention systems and rain gardens and all of those, ours are far uglier, quite frankly, all right? Because we mix vegetation up and we allow some vegetation to die. If it dies, it's not successful, it's not competitive, but we mix it up. And we'll put trees in. If you look at a lot of the Melbourne system, I'm not criticising Melbourne because they're absolute pioneers in this area, but they use monoculture a lot. They'll plant the whole thing with carrick suppressor or with some other sedge or whatever, and it looks really neat. People like it, but it isn't actually as effective as a natural system. And where possible, I try to put in trees. You can't see them in that photo, but this is a photo I took about a year ago. Same system, okay? And in fact, all you see is trees. People who park their cars there just think they're parking them in trees and they moan about the birds a bit, but overall, that's what they think they're parking onto. A bit like Shelley's photograph, that's the system at its downstream point, looking back along that tree line, and that entire car park drains to that biofiltration system. There's no pits, there's no pipes, and unquestionably that was cheaper to build than a car park with pits and pipes. Unquestionably. Okay. That's the slotted curbs that Shelley was talking about, and that used to have, I don't know if you remember the first photograph, it had lots and lots of vegetation. We haven't ripped that out. We do harvest them occasionally to take out the biomass and the nutrients, etc. We don't do a lot, to be honest, but most of that sedge-type vegetation has died. And we haven't replanted it because those trees have taken over that role. They're doing a brilliant job at nutrient removal. The water system's working. There's lots of leaf litter there, but that's okay. And the system pretty much remains untouched. And it still works really well. Those roots are keeping the macropores open. The system's not clogged at all. Has never been replaced in terms of the soil media. That's an engineered soil in there, it's not a natural soil. And those trees are quite happy in the engineered soil as well. So it can be done. It requires thinking outside the square, but it's certainly worth pursuing. And you'll see that as a constant theme about mixing systems up. That is not a biofiltration system that you'll find in many textbooks. Not many people want to plant trees in these systems or even mix the vegetation up too much. That's just the outlet again. Another system we use, which is also mentioned, I think, in Shelley's presentation, it might have been Peter's, is a tree inlet. And this is the tree net system, but there are others. And they're fun to play with. And that's the thing. I know you all think engineers are conservative, but we actually like to have a bit of fun occasionally. So we play around with these systems, right? And we put different media in, and we see if they work, and we see if they don't work. We see which media is the best. And you monitor them over a long period. So I had a PhD student recently work on these systems to see what the best is. But I did actually, I'll be honest, when I first looked at my first ever tree inlet pit, I was a bit cynical. There's the engineer in me, right? And I looked at that and I thought the volume's not big enough. Doesn't matter how much I try, I'm not going to squeeze too much stormwater into that system. But I was surprised. What I wasn't allowing for was those trees sucking up the water and emptying that system reasonably quickly, actually. So I got my student to do all the work for me, which is another characteristic of a good engineer and a good academic. And she did some modelling for me. And this is the results of the modelling. Okay? So the field case that we put in the ground, the one I was cynical about, is case S2. And then the simulations are S3, S4, S5 and S6. So S2 is field data, effectively. And then we calibrated the model and ran it for other things to see how big we could go and how much of the runoff we could try and tackle. Okay? And those are the results. So this is the flow reduction from stormwater runoff. So it's a bit what Peter was focusing a little bit on, but Peter's work was, I think, more complex than that and incorporated some very important facts on points on urban form. But basically, the system could take out, in its small original design, about 7.5% of the mean annual runoff. So that's pretty impressive, actually, when you work out how much that is a year. Okay, and that's calibrated to experimental data, field data, I should say. And then the other ones they're calibrated from that original case, but we haven't built them. But if you can get up to, and this is the most you can get up to, is about 25% with a good design. So that's far from inconsequential. Okay, you're bringing, effectively you can think of that as reducing the runoff coefficient by 25%. And if you could do that in a typical urban development, you're laughing, you know? So there are very promising results from that system. But equally, it's also playing a very important role in keeping trees alive, because you're constantly feeding the tree. And I've probably skipped over a very important point. The reason I err towards those larger vegetated systems is about resilience. Okay? Adelaide gets the longest. I'll tell you something very interesting. I was born in a coastal town on the Essex coast near London. Okay? I then spent 8.5 years at university in Manchester, which is called the Rainy City in England, which is quite an accolade for an English city. Right? And I then moved to Sydney, and then I then moved to Adelaide. So I popped to 4 places. I started on the Essex coast, where the rainfall was 500 millimetres a year. I then moved to Manchester, where the rainfall is between 900 and 1,000 millimetres a year. I then moved to Sydney, where it was between 900 and 1,000 millimetres per year, and I've ended up in Adelaide, where it's 500. Okay? So the city I live in now in Australia has the same annual rainfall as the town I was born in England, and Manchester's got the same as Sydney. So this idea that we live in a dry continent is actually true, but you've got to break that down a bit. We actually get plenty of rainfall if you can do things with it. But what we have that England doesn't have is, well, Bunnings for a start, okay? If I walked into the equivalent of Bunnings, B&Q in England, and I said, I want to buy a rainwater tank, they'd sell me one. And I'd walk out with it under my arm. Okay? Now, if I tried that in Bunnings, they'd laugh me out of the shop. Okay? And the reason is, the minimum size that you guys have is probably about 1 metre cubed or 1.5 metres cubed, whereas literally a big rainwater butt, they call them in England, would be no bigger than this table, probably a lot smaller. And yet, I've just told you the rainfalls are the same. And the difference is, in England, unfortunately, which is one of the reasons I migrated, it drizzles a lot. Okay? And that rainfall falls regularly. Their inter-event dry periods are quite often 2 days. Inter-event dry period. Okay? Adelaide gets the longest inter-event dry period of any capital city in Australia, and in summer it's 7 to 8 days. Okay? Now, if you have vegetation living in a sandy loam engineered soil that has a water requirement, and it's 40 degrees in Adelaide in summer, and you leave it dry for 8 days regularly, and that's the average, by the way, so it can in Adelaide go for 3 months without rainfall, that vegetation doesn't often survive too long. Whereas a tree that is resilient and can maybe tap into deeper water, but even so can still survive fairly long periods, just is able to cope better. Whereas in England you can plant what you like and it will stay green and you'll never need to irrigate it. You do need to irrigate it in Australia, as Shelley was pointing out, but you can irrigate it with grey water, as she mentioned, but you could irrigate it with stormwater. And if you can build these tree pits, or you can wet a permeable paving that takes 5 days to dry out and allow the root access to that water, that's it. You've done it. And you've done it in a multifunctional land use way because you've parked your car on top of it. And that street tree, with its massive root system, you can protect your system from the concept that, this is one of the ones I've been fighting for my entire career, and I will show you some evidence to back this up. The idea that if you mix trees with any form of paver, let alone permeable paver, eventually the roots are going to lift the pavers. Absolute urban myth. And I'll show you the evidence of that. And we've had an Australian Research Council grant where we grew a whole set of trees in an engineered situation, and there was absolutely no movement. And I'm sure Tim, in his presentation, who's done an entire PhD on this topic, will also show you some evidence, and that's what you need to see, some evidence of these systems. And I will explain why roots do lift pavers and asphalt. It's very, very easily explained. And I will also show you how you can stop that happening completely. These are examples. These are all taken by Martin Ely, who's a landscape architect. He's Adelaide based, but these are actually in Sydney. And they're examples of fairly juvenile trees planted into permeable paving systems. Tim will show you some much more recent ones in Adelaide that are probably better designed. This, I think, Tim, is this one of your photos? Yes, I thought it was. In the city of Beacham, I think. And this is one of his systems, and I'm not going to steal his thunder. He's going to show you the outcomes of his PhD, which demonstrate how to build these systems safely and well. Okay? This just shows you a permeable paving system for those that haven't seen it. There's a leap of faith here. Nope, didn't work. How do I start that, Paul?
Hopefully, just click with the mouse.
Yeah, got you. Thank you.
Cool.
Right, that is what we call permeable interlocking concrete pavers. In Australia, by far the most common type. The other fundamental type is porous concrete pavers, and I'm absolutely delighted to see Midland and Brick have bought some specimens here. As far as I'm aware, there's only 2 manufacturers of those now in Australia, one in Sydney and Midland here in Perth. So you've got a very, very good source of porous pavers. They make these as well, but these are made out of standard concrete. They're incredibly strong. That's the other urban myth about permeable paving. If you've got a weak permeable paving system, providing you've used the right thickness paver, it's not because of the paver. The paver can take cranes lifting 4 container stacks at a time with their wheel load. Okay? They're as strong as you get. If you've got a problem with a permeable pavement system or paver system, it's because you haven't designed the base course deep enough. Because all the pavers do, they interlock, the word interlocking's in there everywhere, they interlock, and all they do is transfer the load down, across and down. And they spread it out and it goes down to the gravel, and if you can't build something deep enough with gravel to sustain heavy loads, then there's something missing in the design. Okay? So those are solid concrete, those are 80mm pavers. There's some 60mm ones which are for lighter traffic over there, but have a look at the other type. I haven't got a photograph unfortunately, but porous concrete. I started off looking at porous concrete early in my career and I moved away from it because I thought it had abrasion problems and I thought it was just a little bit too hard. I'm actually coming full circle round because something I wasn't thinking about when I was younger was climate change and urban heat island effects. And those porous pavers have a characteristic that's really hard to mimic unless you're a plant. And that is they hold the moisture close to the surface for longer than that system does. That system dries out really quickly. And what that means is the pavers actually evapotranspirate back out, they evaporate, they don't transpire, but they evaporate back out, and that causes insensible heat loss because you're converting water into vapour, and that has a massive impact in terms of the surrounding ambient temperature. You also get a sensible heat loss because you're actually putting water in something which cools it down, but it's nowhere near as big an effect as the insensible heat loss, which is really hard to measure by the way, but it has a great effect. So have a look at the porous pavers. They're a really wonderful technology if you can get over the abrasion part of things, but if you talk to the manufacturers, they are absolutely full of good data to help you. Okay? So, but that's just a standard permeable interlocking pavement system, and the water infiltrates through them. Now, how do you stop trees from lifting that up, and how do you integrate them successfully? That's what I'm going to focus on to some extent here. So this is a typical normal street tree configuration, and really badly drawn by the way, but if you look at the roots, people always have this belief, and it's because it's true, that the roots will hunt out horizontally moisture below the paving surface. Okay? Now, just think about what happens to the water in that left-hand system. I'll come to the right-hand system in just a second. But think about the water. The moisture in the soil is against an impermeable surface, which just say it's asphalt. Okay? Moisture will condensate or condense underneath that surface. And what the tree will do, and this is where I'm absolutely on thin ice because I've got a bunch of arborists in the room that are going to shoot me down. But here we go. We'll go for it anyway. Right? They'll throw out some fibrous roots, opportunistic fibrous roots, and hunt out moisture. And if they're successful in that endeavour, they'll throw out or convert them to woody roots. And those woody roots are the ones that lift the pavers, or the asphalt, or anything else. Okay? I'm looking forward to question time after that statement. Anyway, that's what happens in that case, and that's why we see so many examples, and Tim's going to show you lots of, I think I might even have a few in this presentation, of asphalt being lifted. And it's much more common actually in asphalt than it is in paving systems. But it still happens in paving systems if the paving systems are impermeable enough, because they do exactly the same thing. They have moisture close to the surface and the roots hunt them out and they're happy. If you can encourage those roots not to go there, or if they go there, they die, they desiccate and wither, and the only water they can find is downwards, they'll follow that instead. And that's the concept over there, and that's what we undertook the Australian Research Council grant on, planting a bunch of those, and I'll show you some photographs in just a second, to see whether we could get the roots, the root architecture into the form we want it in. Okay, now it will vary, I've got to say it will vary hugely from species to species, but for the species we used, it worked. Okay, and what's doing the work here is two things. One is we're removing moisture from that underlying layer, first of all. Okay, and that's the primary aim that we were looking for. But the second thing is we're putting a free draining gravel, and a reasonable amount of it, above the root layer still, so that if the roots do try and penetrate that, A, they have a really, really hard job doing it, because that's compacted gravel, and B, it's free draining gravel that can drain upwards or downwards. It can go sideways, but it tends to go upwards or downwards. Okay, it either evaporates upwards, if it's close enough, and it'll be the very upper layers. You'd be surprised how quickly evaporation dies off as the deeper you go. Okay, or more likely it will drain vertically downwards. And here in Perth, where the underlying soils are very permeable, that is just a fantastic system. It will just permeate down really, really quickly. And that means that if it throws out roots and they do manage to penetrate that gravel layer, they will desiccate and die very, very quickly, because there will be no moisture there very, very quickly. So you've removed the need for the tree to hunt out water in that area. And over long periods of time, they will form an architecture that reflects that. Now the trouble is, I go back to a point I made about all paving systems and all tree systems actually. I can show you those diagrams till I'm blue in the face. You go out on a site, you won't see it. You'll see the ground surface. You'll see the paving system. You'll see the tree. You'll see the bottom of the trunk. You won't see the tree roots. You won't see the layers that we've engineered in there. And that's the problem. Unless you're there and you see it, seeing is believing, you don't know what's actually happening under there. And in fact, even worse than that, even if you design it and even if you believe in it, you don't actually know, unless you're on site, whether it was built to your specification. And then it only takes one of those where you think you've designed it well and you think it's working well, and it's not, the pavers lift, and in the end you go back on site and you find the contractor did actually lay sand and not gravel, because it was cheaper and that's how they've always done it. And you weren't there, and you don't know, and everyone loses faith in you. Okay? So it comes back, I'm sorry to repeat, but it comes back to the basic concepts I was talking about right at the beginning of this presentation, about building up a body of evidence that is robust and resilient like the systems you're trying to design. So these are some systems that, that concept I was showing you there, should have said it, involves largely planting juvenile trees with immature root structures and training them. The other approach you can do, and this is an example of this in Macquarie Park in Sydney, is you can take mature trees, fairly mature trees, and build paving systems around them. Now the disadvantage of doing this, the advantage of doing it is you're not planting new trees and you're not changing the urban environment too much, and you're providing those trees with more water so they will grow better. The disadvantage is you're building it around it, so the root you're having no influence on the root architecture largely. Okay, so but it's another way of doing it, and those permeable paving systems are still working today, and they still haven't lifted as far as I'm aware, and that's because I think the architecture of the root's already formed. It's not going to, doesn't need to hunt out particularly more water. It's getting plenty more water from that permeable paving system that it didn't have before, so it's a happy tree. Okay, so that's what I think is happening there. But that is the alternative. It's not a great, you haven't put a lot of creativity into the engineering design of that, but it still works, and it's certainly better than having a tarmacked area there. Okay. The albedo, by the way, I'll come to it later, but the albedo of those pavers is about 25 times higher than asphalt, which means it reflects 25 times more. That's the system close up. That's a Eco Trihex by Arbor, I think. This is just to show you they do this elsewhere in the world, and the presentation I gave last week in Adelaide was about all the different world practices. But I've just picked out one just for example. This is in South Africa, in Durban, my favourite South African city, by the way. And this involves a whole suite of both permeable and impermeable pavers and a detention tank. It's probably the most engineered, over-engineered system I've ever seen. I didn't design this, I went to go and have a look at it. It's well over-designed. These South Africans are brilliant engineers, by the way, but this is a little bit over-designed. These are the photos that, this is one Tim gave me, and this is where they've asphalted up to probably a juvenile tree at the time. There's plenty of condensate underneath that asphalt for long periods. The tree roots have found that water and grown and pushed the asphalt up. So when people say this happens in pavers all the time, it's not. It happens far less in pavers, because pavers, even the best laid pavers, are slightly permeable, whereas the best laid asphalt is pretty impermeable. Okay, it happens more in asphalt than it happens in any other material. Asphalt is, if you've got a bunch of engineers around a table and said, design the worst substance in the world ever, asphalt will probably be right up there. Okay, it's got a terrible albedo, it's way too cheap, and it's just a nasty material. It leaches toluene when you lay it, which is carcinogenic. It's just we haven't got any tarmac manufacturers in the room, have we? It is really a really bad material. This is pavers doing the same thing. I'm just being honest here, showing you some photographs of the same thing happening. And this is where they're paved up to probably a juvenile tree again, and it's done exactly the same. Okay, so no different to the asphalt. There's another one. So how do you stop all this happening? That's what I'm going to focus on a bit now. This is the Australian Research Council experiment in Queensland on the Sunshine Coast, and it is a no, it's going to sound big-headed if I say it's a really well-designed experiment, I'm going to say it. All right? And what it has is exactly the same tree species planted in asphalt, planted in permeable paving, and then a control, well, 4 controls actually, with no tree at all. Okay? And then the movement of those pavements, the moisture underneath those pavements, the growth of the tree in many measurements was taken over a 4.5-year period. It's the most extensive longitudinal study of this taken to date. I would like the ARC to give us more funding so we can carry this on and measure this, because what would be the concept of getting us all together and working for the best for the community would be to run this for 25 years and see what really happens. But we didn't just run it and look at it the way we're looking at it now. Remember I said you can't see what happens underneath? Every so often we dug one up and we looked at the root architecture. We looked at what happened with the gravel. Had the roots penetrated the gravel? What had they done? Which is similar. Tim did his PhD after this. This started in 2012. Tim, when would your PhD start?
Mine was part-time,
yeah.
09 to 14.
Okay, yeah. So Tim's got some fantastic pictures of those fibrous roots and the large woody roots. But I'll show you basically a bunch of engineers excavating these systems out, and there you go. Right, top left, we'll go around. Top left is one of the trees in asphalt. Okay, next to it is that excavated, I think after 2.5 years, I think. Okay, and you can see exactly what that root architecture's done. That has hunted out that condensate, it's found it, it's thrown out some large woody roots, and bang, it's a very happy, stable tree, but not a very good pavement. That second one, I forgot to put the photo in. You'll have to guess from those feet in the top left-hand corner. That second one is after 4.5 years in a different system, in a permeable pavement system. Now, can you see, and it's the same tree, can you see any of those horizontal roots in that bottom one? There's nothing there. what's happened is the trees had to stay, it's had to throw out roots because roots have a structural purpose to keep the tree standing up. So it's had to do that, but it's hunted out the water at the same time, and it has thrown out that root system there, which hasn't dislodged a paver by more than 1 millimetre. Okay? And exclusively, that's what we found in all the systems. Well, we didn't dig all the systems up because we wanted them to continue so we can monitor some for over 25 years. But we dug over half of them up. And that was the evidence we found all the way through. Now, I've only got so much time in this presentation. If anybody wants me to send you the paper, well, there's 3 or 4 papers that came out of this, but a paper that shows you the results of all of those, I'm very happy to. Okay? And in fact, you can download that paper from the CMAA website as well. Most of our research goes up on the CMAA website once it's published. Okay? CMAA is Concrete Masonry Association of Australia. Now I'm going to talk through some heavy engineering applications, just to, and these focus a bit more on the permeable paving side rather than the tree side. But I just want to explain the terminology, because this is something we do really badly, and that is, if you look at the left-hand terminology and the right-hand terminology, A, they both look like gobbledygook, and B, they both look like each other. They are fundamentally different. The left-hand side are interlocking concrete block pavements, which are impermeable. They're made from exactly the same material as the stuff on the right-hand side, which is a permeable interlocking concrete pavement. I'll tell you why that terminology has arisen, is because the industry and people like myself have always insisted on getting the word interlocking in there. Get it in there, get it in there, get it in there. Because people think that these pavers work in isolation and that they're not strong and that they'll break and crack and whatever. They're not. They act like a flexible slab. They interlock. I could show you a video of us in the laboratory lifting a square metre of these up with no interlocking bedding material between the gaps, and the whole thing lifts up and not one paver falls out. It's a well-studied mechanism of rocking and rotation, and what happens if you think about 2 pavers, I'll try and explain this, I'm not very good at this. If you have 2 pavers like that and you allow one of them to move like that, something's got to give on this side, and ultimately you're going to have a concrete thrust block at the end that's going to stop any movement. So as soon as this starts to wedge, this one locks it, and then the one next to that gets locked. It can't move, because to move it's got to move horizontally. It's a horizontal thing because it's got a ton of, way more than a ton actually, of gravel underneath it, so it can't move vertically. So even that vertical rotation's difficult, but even if it wants to do that, it has to push every other paver along, which it can't do. Okay? If you put in those gaps, I'm colourblind so I can't see the spot I'm about to show you. If you put gaps, if you put bedding material into those gaps, which is what they should be, okay, that interlocks it even more, so it is impossible for it to move. But if you take that out, it still interlocks. Okay, so these systems are strong. So the reason the terminology is a bit confusing is because we always insist on the word interlocking in there, and that's a very important concept, right? So the left-hand one, there's nothing I can do about that. That's what it is. The right-hand one, we do abbreviate. We just call them permeable pavers now. Okay, so permeable pavers and that. Fundamentally the same piece of concrete. That is a laneway in Grange in Adelaide, and that's the system. And I like this one picture because and this is my concept again, get the engineer or whoever designed this out on site, watch it being constructed. Check there's not sand anywhere near this system. Okay? Seriously can't see that. I'm trying to point to the bottom bit. I'll walk over it. That's your base course, that's your bedding material, that's your paver, that's that block that I said probably plays the most important role of all, because it stops any lateral movement. Okay, if you haven't got that on both sides of your permeable paving system, in fact all 4 sides, the system won't work. Okay, very, very important. Okay, and don't sit that on sand, because that will move. Okay, that must not move a millimetre. Okay, so those are your 3 layers, and it is a multi-layered system. And the reason you can't, by the way, I'd be a rich person if I could patent some of the designs I've done in the past. You can't patent anything in that set. Well, paving manufacturers will argue with me, you can probably patent the pavers, but that's it. Because the other system is just gravel or a piece of concrete. Okay? So this system is very, very cheap and easy to construct. And the reason we give out all of our information, all of our software, all of our papers free of charge is because we can't make money from them. No, it's not. It's to get the information out there. And I'll talk about the software that's behind this in just a moment. Okay? So that's how this is. So the left-hand side, which I think is Moorebank in Sydney, notice in the background the sand. And this is, I'm going to sound like a scratch record here, but most contractors don't lay that right-hand side. They're beginning to, but most contractors have no experience with that. They have loads of experience with that left-hand one. So when they get a young engineer or a young landscape architect telling them to put it on this bedding gravel of 2 to 6 mil, which is a lot harder to source than sand, and they've laid 99 systems on sand, they either think the engineer's made a mistake and specified it wrong, or they think they don't know what they're doing and sand will work better. And I have seen so many permeable paving systems, early ones mainly, go down on that stuff. They will clog within a year. And most of the urban myth around clogging of permeable pavements is because of that practice. Either that or putting in a geofabric layer, which used to be common practice, and I'll blow that myth out in just a moment. Just a moment. Sorry. That stuff used to have a geofabric between that and that. Okay? Anybody remember that? It's very early practice in permeable paving in Australia. We don't do it now. I'll explain where it came from and I'll explain why you shouldn't do it. It came from the fact that a lot of American practice, South African practice, and even some European practice used to use much larger base course material, up to 60 mil in diameter. The South Africans actually use it up to 100 mil in diameter because it's cheap rock. And similar bedding material, South Africans still use a lot of sand actually, but the Americans have always used good material here. But they've got much larger aggregate than we've got, and there's a 10-to-1 ratio that dam engineers use all the time. If the average aggregate size has more than a 10-to-1 ratio difference, the small one will migrate into the big one. So the old permeable paving systems had more than 10-to-1, so you had to put a geofabric layer in, otherwise this stuff washed into this stuff, and you get slumping. That's where it came from. Okay? That is now 20 mil or 20 mil graded, very rarely bigger than 25 mil. That is 2 to 6 mil, 2 to 5 mil. It's specified differently. It depends on what your local suppliers can provide, actually. But it's typically 2 to 5. Less than the 10-to-1 ratio. Not a bit of that can migrate into this. So all a geofabric does is create a slipping plane. So if you put there's two things it does actually. One is, if I gave you a piece of carpet, think of that as geofabric, and told you to bury it in your backyard, and then dig it up a month later, what do you think you'd dig up? A wet, soggy bit of carpet. So one thing it does is it holds on to a lot of moisture, which is good from a bacterial growth viewpoint, but not good for too many other things. Okay? Second thing it does, it creates a beautiful slip plane. So if you've got a hoon doing donuts with his car onto permeable paving that's got a geofabric that far under the surface, that geofabric acts like a slipping carpet, a magic carpet almost, and the hoon's having more fun than it would have done, but the pavers are also moving hugely. Okay? So that geofabric is a legacy thing from old practice, no longer needed. You'll see it in none of our papers, you'll see it in none of our guidelines. There's still one manufacturer, I'm not going to name and shame, but still one manufacturer that hasn't bothered taking it out of their guidelines. So you will actually see it in one manufacturer's guidelines. Most of the modern thinking manufacturers have now removed it, and most state guidelines have removed it. But I just wanted to explain that, where it had a good, reasonable, perfectly logical reason for being there 20, 30 years ago. It has absolutely no place now. thought I'd put that in to make you laugh. There's geofabric. Now that's a very, very early system, and it's a demonstration system, but it does show you the pavers, the bedding course, the base course. So the one I've just told you not to include is that one. Showing you this because it comes back to a very important comment that Peter made about design tools. That is a flow chart that an engineer has to follow, or a landscape architect or whoever's designing it, if they want to build not a permeable paving system, but a interlocking concrete system, which is the simplest paver system to design, and that's the simplest design process they can follow. And guess what? That takes a long time to churn out a design. And then if they want to iterate and change it subtly, they have to do the whole thing again. And that's why the CMAA came to the University of South Australia and asked us to write a computer program for this, so it just takes away the pain. Okay? And the program that's available is now the most sophisticated design software in the world for both interlocking concrete pavers and permeable pavers. It uses a very complex mechanistic design. It includes the British port method, so you can design heavy industrial pavements as well as residential and commercial, and it's all done at a touch of a button, and it's free of charge. We do give out all our software free of charge. Okay? So you can download it from the CMAA website. It's called Design Pave. And for those that remember the old softwares, Australia was one of the first countries to generate any software in this area. There's a guy called Brian Shackle, professor at the University of New South Wales, did some absolutely pioneering work. He wrote the LockPave program. You may have heard of LockPave. It's no longer available. And Design Pave was commissioned to replace that because Brian would have probably been the best person to write this, but he sadly passed away a few years ago. And so we inherited the job of creating a new software package. LockPave was very empirical. It involved a lot of experimental results from studies that Brian had been involved in. The research has come internationally a lot further since that time. So this isn't empirical, it's mechanistic, which means it's theoretically derived all the way through. Okay? So that's the structural side or the geotech side. And then the hydrologic side used to be in another software program, which you might also remember, called PermPave, which we, University of South Australia, did develop the original PermPave, but it was a pretty basic program, quite frankly. This now, the PermPave element to Design Pave, it's all, you get one piece of software and it's all done through one interface. But the PermPave side of it now is being updated for the new AR&R, Australian Rainfall and Runoff, so it has the latest hydrological information in there. It's done for any location in Australia. You pick your location, it downloads the data, the rainfall data, and it runs the simulations for you. It does it all. Okay, so and it's free. They only released it earlier. Sorry, I think it was late last year. Is Keanu in the room?
Yep.
When was it released? I know you're going to present this, so I'm not going to steal your problem.
July 2018.
Okay.
Yeah.
And you've had 700 downloads?
I think about 800 something.
800 downloads. Okay, so most of the major consultancies are using it now. A lot of consenting authorities to check work are using it because you can literally check a design in seconds. Keanu's going to talk about the program, and I think we might be running something for CMAA in terms of demonstrating the software if people have got time. I don't know if that's going ahead.
Tomorrow.
It is definitely?
Tomorrow.
Great. I'll leave you to talk about that, Keanu. Okay. Good. So that's the website you can download it from, which is the Concrete Masonry Association's website. It's also the same website where all of our journal papers are uploaded, all of our findings and anything else that we want to get out there, we normally channel it through CMAA. So, I realise I'm getting low on time. Just talk about a couple of big projects. This is King William Road, which at the time it was built was the largest paved road road with pavers in Australia, in Adelaide, 3,000 square metres. Briefly mention a much even bigger project, which is Lexington Bus Depot, which is built to service the new Badgerys Creek Airport in Sydney. That's an incredibly innovative design. And the Moorebanks IMX, the import-export terminal at Sydney, that's got permeable paving where you've got cranes lifting containers onto ships and onto lorries. So you can design these systems to be as strong as any other system. They're used at airports in Europe. They're used on the heaviest industrial applications, and the design pave software, as I mentioned before, has that design method in it, which is called the British Ports Design Method, which is a separate design method to the commercial and residential designs that you would put in for your typical developments. So that software can do everything from a residential house up to a container shipping yard. Okay. This is King William Road, I love these photographs. This is it being dug up. That's there. Sorry, not a tree in sight, Rob. They did plant some trees, but there we go. That's it after completion. It's just been relaid after it was designed for a 20-year life, and it was relayed after 35 years. Okay, so it shows you these systems, their design lives are very, very long indeed. This is Lexington Bus Depot. This incorporates all sorts of innovations, including permeable pavers next to pavers. One of the things I try and tell people is not to try and pave the world, although this is a really bad example to show you because they did pave the world with this one. But you can actually use an asphalt surface to run on water onto your permeable paving surface. You can go up to a 4:1 ratio, and that 4:1 ratio means you can have 4 times as much asphalt draining onto a permeable paving system and still have no pits and pipes. If you go above 4, it's actually not the hydrological load that makes the project suffer, it's actually the sediment load. If you drain more than 4:1, you get too much sediment coming down the system, and the system clogs beyond the design life. But you can design a permeable paving system to fully clog over its 25-year life. You can size it, and you can do it using the software so that you accept it's going to clog, and if a council says to you, I don't like permeable paving systems because they clog, you say, right, I will design you a system that will clog. But it will still take the hydrologic flows up until its 25-year life is exhausted. Okay? And then I'll send somebody out to lift all the pavers, brush off the bedding material, put fresh bedding material, put the same pavers back down, and you've got another 25 years. That's how cheap these systems can be. So that's the system as constructed. Is that the video one?
Yeah, if you click the mouse.
Just quickly. I might have to cut this short if we run out. Thanks,
Yeah,
Paul. Thanks, Paul. I wanted to show you this because I wanted to show you how pavers are laid today. Vic's here, originally from Holland. The Dutch have been using these machines for years and years and years. Australia hasn't had the large-scale projects in the past to warrant using them too much. They lay 1 square metre at a time, and that enormous paving system was laid in a few days using those machines. So in a second, it's only a 2-minute video. There we go. So these are the permeable ones going in. Sorry, these are the impermeable ones. The permeable ones are in bays over there. So that's the sand because it's impermeable. And that's what it looks like when they're laid. Same machine lays the permeable ones. And those guys basically just knock any movement out of them and then put the bedding material in. As the bedding material is the same material that goes in the interstitial space between the pavers. And unfortunately that is paving the world, but it is a bus car park. There's your storage system. Notice how deep that gravel is. That's actually a harvesting and reuse. Something I should have mentioned with the software. I'm sure Keanu's going to mention it. The software can design for. Shelley was mentioning that, you know, people think it's all about just flood control, and it's not. It's not. I agree with what she said. The flood control is one, water quality control is another, water harvesting and reuse. The design pave software can design for all 3 of those. And then, unlike before you had software where you'd have to design it 3 times, you can do it with the click of a button each time. So you put the same design parameters in, you click for water quality control, see how much pollutants it takes out, click for water harvesting and reuse, how much harvested water you can reuse, click it again, and you can get the flood control. Moorbank IMX, this is the heaviest duty application I've seen in Australia to date. There's a larger one in the States. This is the pipe. All right, thank you, Paul. Stop mine as well. This is a permeable pavement system that we built at the Mawson Lakes campus, University of South Australia. It's a standard car space, 5 metres by 3 metres. It's a 4,000 litre rainwater tank that you park your car on, multifunctional land use. Done with permeable paving. There is no tank. It's just a 1mm polyethylene liner filled with the same aggregate you'd have, but deeper. It's 1 metre deep. The water is harvested. Those are just water quality results. After 24 hours, dissolved zinc is completely removed. Excavation, $500. Gravel, $450, of which was given the excavator to site. Gravel, $260 to $700 if you want to put granite in there, but $260 is the dolomite. There's the liner, $400. That's the system. Total material cost $2,200 per car space. If I gave you $2,200 and said go to Bunnings and buy a rainwater tank, would you come out with a 4,000 litre one installed? No. So that's where multifunctional land use comes into play. We decided to see what we could get that to work in it, and this is one of our really ugly systems. We built a rainwater garden exactly the same size. We irrigated it from a solar pump. There's no electricity on this site, there's no municipal water on this site. If we get the calculations wrong, the system dies. That's the system just after planting. That's the small solar pump. Literally, the solar panels are the size of this computer. If you go more than a metre down, the size of the solar panels goes up exponentially. So we never recommend going deeper than a metre because you need 2 metres of head, 1 metre the actual depth you're pumping up, 1 metre to get it through the irrigation pipes. Because you need 2 metres of head, and that's the size of the solar panel that would do that. That's the system today. That is 9 years after we built it, and it has never had municipal water added to it. It's never been hand watered. A lot of plants have died. You wouldn't believe it looking at that. A lot of plants have died, but we haven't replanted either. And that's why it's a bit more uniform than it was when we first planted it. Okay. I forgot to mention, there are see those 2 pipes in the middle and at the end? They're soil moisture sensors. They switch the pump on. We don't monitor it. We don't do anything. We maintain it every few years just to check everything's running. But basically that's a self-sufficient system. So 1 car space can keep 1 rainwater tank the same size going ad infinitum at no electricity cost and no water cost. Now if you scale that up to your urban developments, you're looking at some of the concepts that Shelley was talking about, except a sustainable one where you've got no long-term maintenance effectively. Just point you to this. This is also downloadable from the CMAA website. It's the most comprehensive life cycle cost analysis of any paved systems in the world. Very, very clever. They took 250 projects in the UK, about half of which were asphalt, half of which were permeable paving, and the half that was permeable paving, they redesigned them for asphalt. The part that were asphalt, they redesigned them for permeable paving. Okay? And then they did a cost-benefit analysis to see which are cheaper, and that's the results. Okay? The initial costs are cheaper for asphalt because asphalt is a cheap, nasty, horrible material. Okay? A whole of life discount rate of 5%. Permeable concrete is way cheaper on all 200, well, on the average of 250 projects. 10% discount rate. Permeable paving is still cheaper. You've got to go to a 15% discount rate before asphalt comes back into play. And that's largely because those systems have no pits and pipes in the permeable paving system. And that's where the majority of the costs are on that type of project. Okay? So I strongly recommend you to get this. A free copy. 2006 it was published, I think, and really, really good reference source. I'll finish here. Urban heat island effects. Basically, asphalt's black and permeable paving and paving isn't. That's really the end of the story. Okay. The albedo for concrete effectively is 0.25. The albedo for asphalt is 0.1. 25 times more reflectivity, and therefore much better urban heat island. There's the experimental results just to back that up. That's both night and daytime. The blue is the sensible heat, so that's what you feel, temperature, and the nighttime sensible heat is in the other one. Just think in the back of your mind 3-to-1 ratio. All those figures are 3 to 1 ratios. The asphalt is 3 times better, 160 to 450, 40 to 120, 3 times better. Okay, the albedo might be 25 times better, but when it comes to actual measured temperatures, it's a different thing, and it's 3 times better. And I've recently updated this. This is a paper I wrote a long time ago, and I'm engineers conservative. I estimated 20 kilograms. I've talked to a lot of arborists since then, and they use 20 as the lower end of the range. It's 20 to 100 kilograms of carbon dioxide that you can sequester in these systems. So I'm a bit out of date with that one. So I'll finish there by saying the traditional approaches to water resource management will present major constraints to new development. This is already being exacerbated by climate change. In my view, the future lies in multifunctional land use. That means bringing in experts from different disciplines and working together, which has been a common theme in the 3 presentations this morning, 4 presentations, sorry. And then the impediments include pretty much the same ones that the City of Adelaide identified for trees. We face them with paving as well. Okay, thank you.